Hello and welcome to the video. In this video we will explore the stack structure in assembly programming. We will look at how a stack frame is created, how it works and how it's removed. On the left we have a simple C code example, on the right we have a visual representation of the stack. At the bottom we will see our simple C code turned into assembly code step by step. Before we begin, there are three important registers we need to know: base pointer, stack pointer, and instruction pointer. The base pointer shows the starting location of the current stack frame. The stack pointer always points the topmost element of the stack, and the instruction pointer holds the address of the next instruction should to be run. So, let's begin. Here we have three assembly commands. We will start by looking classic process of building a stack frame. First, we push the current base pointer to stack. We are now looking at the stack state after these three commands have been run. So we push the base pointer and it's now on the stack. We copy the address pointed to by stack pointer to base pointer. The last element in previous state of the stack is now pointed to by the base pointer. We subtract a 16-byte array from the stack pointer to make space on the stack. But why we do subtract? Why we don't add? Because the stack grows from high address to low addresses. That's why we subtract. It's kind of confusing, but something to pay attention actually. Now we are in state before function 1 is called. In next step we will assign the arguments to call function 1. After that we will call function 1. By now we have already created a stack frame for the main function. This area here between RBP and RSP represents our stack frame, and currently we have one such frame for main. It's 16 byte size. Now function 1 has 8 arguments and we need to assign these 8 arguments. Here there's a concept, it's kind of important for us. It's called caller and callee rules. And if we are talking about the 64-bit, we must place the first 6 arguments of our function into the register. And we must place them into this register in specific order, so in normal sequence, I mean. But if we have more than 6 arguments, we must push the rest arguments onto the stack in reverse order. So for arguments 1 to 6, we assign them to the register. Then starting from 8 and 7, we will push them onto the stack in reverse order. And as you can see, now appear in stack. After making this argument assignments, we can call function 1. We call function 1 with the instruction call function 1. This call is actually a spatial instruction. We will talk about that how before we move on. But as you can see, we meet again these 3 lines we looked in first slide. This time, however, we are creating a stack frame for function 1, not for the main function. So again, we push our base pointer onto the stack, then we copy address pointed to by stack pointer into the base pointer. And once more, we open the 60-byte area by subtracing from the stack pointer. This region is now stack frame that we created for function 1. When we assign the base pointer, we can already see it, but we have also another value here that we can call the return address of main. We have not yet explained how this value appeared. We should explain that with the call instruction. If we show it again with pseudocode, it first opens an 8-byte area from the stack pointer. That's one box. Then we copy the value of instruction pointer to stack pointer. In other words, we push it onto the stack. So what does it mean? As we explained in the first slide, the instruction pointer tells us where we are in our code in assembly. We do this because when function 1 finishes, we will return to main function and we will continue from where we left off. If we don't save where we left off, we will not know from where we should continue. In that case, either we should have to start code from the beginning again, which would make no sense, or in a simple words, our code will not run correctly at all. That's why, with the help of the instruction pointer, we push the point where we left off onto the stack as a return address of main. After that, following the call, we push the base pointer as well, and we form our new stack frame with new stack pointer. Now let's continue. This is the time we are going to create a stack frame for function 2. But before that, we need to prepare the argument assignment for function 2. In the RDI register, we already have our first argument, which is value 1, so we don't need to touch it. We only need to assign G, that's it, the value 7. So to do this, in this line, we get it by taking the value at an address 2 boxes, that is 2 8-byte slots above our base pointer. Let me explain this here so it doesn't cause any confusion. When we look at stack through the base pointer here and see something like, it may look as we have assigned the base pointer of the main function, but that's not what's happening. The stack diagram on the left shows how the stack looks after all the assembly operation we see have finished. However, right now, we are at this point in the code, and while we are at this line, the base pointer actually pointing here to the location indicated by mouse cursor in the slide. 2 boxes above that, we find the value 7. After that, we once again run call function 2. This pushes the return address of function 1 onto the stack. Then we push RBP onto the stack as well. We copy the address currently pointed by the stack pointer to the base pointer. And from the stack pointer, we create a 32-byte area. After that, we prepare the necessary operation to call the printf function. We call an external function in exactly the same way as we call our own functions. So, and this, we have also created the stack frame for function 2. From this point on, the other operations are about the destruction of the stack frames. We will see this in next slide. Now function 2 has run printf, it has printed to screen, and we are going to return. We have 2 special instructions called leave and return. These leave and return instructions are especially the exact opposite of the call and the sequence of instructions we use to build the stack frame. The push RBP, move RBP RSP, and the sub instruction. So what we do? First, we assign the address pointed to by the base pointer to the stack pointer. For example, here there's a stack pointer is pointing at this location. If we look at previous slide, we can see that the stack pointer was set to the address that the base pointer was pointing to. After that, we pop the value of the base pointer. In other words, we pop the base pointer of function 1 shown here and place it back into the RBP. So RBP returns to its old value. At the same time, when we run return, we assign the return address of the instruction pointer. We pop these 2 values, the RBP and the return address from the stack. One of them is placed into the base pointer and the other is placed into the instruction pointer. And in this way, we return to stack frame of function 1. It's like if we had never created the stack frame of function 2 at all. We do same operations for function 1 as well, and then we do them again for the main function. Nothing changed, the logic is always the same. Leave and return, same instructions, and again this frame is removed. Then we do same operations for the main function. There is a small mistake on the slide here. This part should actually say function 1. After we have done the same for main as well, we run return 0 and our code finishes. I hope this has been helpful. If there's any point you didn't understand or I made a mistake, please don't forget to mention it in comments. Take care of yourself. Have a nice day.